Hi there! If you think about a way of multiplying vectors, it turns out that you have several possible definitions. Until now, you have seen you can multiply a vector and a scalar to obtain another vector. In the previous lesson, you learned about the dot product, an operation on two vectors having a scalar as its outcome. Another name for the dot product is the inner product, by the way. This product is closely related to orthogonal projections. In this video, you will find out about another operation on two vectors, whose result is another vector having some nice properties. This operation is called the cross product or the outer product. Let's think about the following question. Given two vectors u and v in three-dimensional space, find another vector w that is perpendicular to both of them. How can you find it? Not a difficult question to answer, you would probably say. You know, after all, that this vector then should have the property that the dot product with both vectors equals 0. For our example, this means you have to solve the following two equations: minus w1 plus 2 times w2 plus 2 times w3 equals 0, and w1 minus w2 plus w3 equals 0. Okay, this is not a problem, except that you now have two equations with three unknowns. You may not know how to solve such a system yet, but in a course on linear algebra, you will learn how to do this. Furthermore, you will discover that there are infinitely many solutions, because if you multiply any non-zero vector that is perpendicular to the two given vectors by a non-zero constant, you get another vector that is perpendicular to the two given vectors. And this you can do forever. You just change the length of the perpendicular vector. One thing you could do to try to overcome this non-uniqueness is to restrict your attention to unit vectors. But even then, you see that there are still two possible directions in which the vector you are looking for can point. To choose one of the two directions, there's a nice rule called the right-hand rule. If the fingers of your right hand curl from u to v, then your thumb points in the direction of the vector perpendicular to u and v that we will choose. This vector is the cross product of u and v. So, if this is u and this is v, then the direction of the vector you are looking for is this way. But if this is u and this is v, I have to put my hand like this, and you see that the vector points downwards. To get the point of this rule, you should really do the movement yourself. Fortunately, there is a procedure to compute the cross product that is really straightforward. I call it the Amsterdam method, because it uses crosses just as on the famous small pillars that can be found in Amsterdam. Let's do an example with our vectors u and v. Write down a table with 2 columns and 6 rows. In the first 3 entries of the first column, you put the vector u, and in the next 3 entries, you do this again. Then do the same thing for the second column, but now with the vector v. Then remove the first and last rows and put 3 crosses in the table as shown. Now compute the 3 components of the new vector w using the crosses in the table. Each cross means upper left multiplied with lower right minus lower left multiplied with upper right. If you practice this in the exercises, you will find out that this Amsterdam method gives a fast way to find the vector w. A quick check will reassure you that the vector w is indeed perpendicular to both u and v. The cross product was introduced by the famous British mathematician Rowan Hamilton in the early 19th century. In general, the formula found from the Amsterdam method to compute the cross product of the vectors u and v is shown here. I now challenge you to prove for yourself that the vector w is indeed perpendicular to the vectors u and v. Given two vectors u and v in three-dimensional space, you know how to find the direction of the cross product using the right-hand rule. The length of the cross product may seem somewhat mysterious still. This length, though, has a clear and nice geometric interpretation. If u and v are not scalar multiples of each other, they actually lie in a plane. A plane is a two-dimensional subset of the three-dimensional space. Then you can define the parallelogram spanned by u and v. This parallelogram then has an area. And guess what? This area is equal to the length of the cross product of u and v. Knowing how to compute the cross product is one thing. The question, of course, is why on earth would you want to be able to do such a thing? Well, there are numerous applications in physics and in mathematics. In physics, for instance, you encounter it in electromagnetism and mechanics on rotating bodies like the Earth. In mathematics, the cross product is used to compute the volume of a parallelepiped and to determine the equations of planes in three-dimensional space. You will learn more about computing these volumes and planes in the next videos. But first, do some exercises to compute cross products and study the properties of the cross product listed in the text following this video.